but well, we'll talk a bit about models as well. So yeah, so first, just going back to the basics. So what are we talking about? What kind of planets are we dealing with? So if you look at this plot, well, most of you know this plot, I think. This is the sample of planets that we have discovered thus far, so semi-major axis and planet mass. And actually the planets that we are finding with the direct image methods are here. So there are giant planets far from their stars, so there is no significant irradiation from the host star affecting the atmospheric chemistry. And actually these planets, they are young. So because when the planets are young, their radius is much larger than what they will, what it will be at the age of the solar system, and they are hot. So meaning that large radius and hot temperature means higher luminosity, and then the contrast between the host star and the planets is reduced. So basically, young planets can be detected more favorably. And well, this means that the surface gravity of these young planets will be very low, in particular compared to the brown dwarf that has been characterized for the last 20 to 30 years. And so this has some implication for the atmosphere. So the two classes of objects can share the same effective temperature, but the surface gravity will be fundamentally different. Okay? So I'm talking here about the vast majority of the brown dwarf that have been studied thus far. The other possible difference between the planets we are studying and brown dwarfs concerns the composition of the planets. So if you look at the transiting planets, some of these transiting planets have measured density, and well, the density gives us information about the content in heavy elements of these planets. So if you suppress, you keep aside all the inflated planets due to the strong irradiation from the host star, you can have this kind of curves where basically there seems to be a trend between the heavy element enrichment in the planet with their mass, actually an anti-correlation. So massive planets seem to have less heavy element content than the smaller one, but on average they have higher, they are metal enriched with respect to stars. So this is what is happening at short separation, so below 5 astronomical units. And at large separation, as you know, there can be several formation mechanisms, and several groups of theoreticians have predicted what could be the heavy element enrichment, in particular in the context of the solar system, where Jupiter and Saturn have some metal enrichment. And so here, this is simulations for the gravitational instability scenario, where the team has produced several predictions for the heavy element enrichment for different disk properties. So one detailed disk curve, but this is just telling you that for the planets that we are seeing with the direct image method, and that could have been formed by the gravitational instability scenario, you are also expecting some metal enrichment. And the big question is whether we can also find this metal enrichment into the atmosphere, whether we can find this something nature like that. And finally, planets that are formed at large separation will be formed typically after the snow line and in between the CO and CO2 snow line, or even beyond these two snow lines. So this has some implication for the composition of the material that is accreted during the runaway accretion phase, typically in the envelope of the planet. So if you look at this plot, you see that if you go from the star and go in the external part of your system, these curves are showing the abundance of the oxygen, carbon, and nitrogen in the midplane of a circumstellar disk, and in the gas phase and in the solid phase. And you can see that when you are crossing the snow lines, the elements gets condensed into there is a phase transition basically, and so the abundances of the gas phase are changing. And they are changing also with time because the disk is evolving. Okay, there is more and more material falling into the midplane, condensing. And so this means that depending on where and when the planet will form, it is possible that the planet will then have a very different atmospheric composition, and in particular, these elements might be tracers of the time scale for the formation, and also on the detailed way the object form and what material it accreted to form its envelope. So just to say that the atmosphere of the giant planet that we are finding with the direct imaging method can have non-solar composition. So how do we study these objects? So actually, the first, I think, fundamental study, breakthrough results that have been obtained with the direct imaging method was the discovery of this 5 Jupiter mass object around a brown dwarf in 2004. This was actually a discovery by the team in Grenoble. And actually, you could see already from the data that we had in hand, which was obtained with low-order adaptive optics system, you could already see that the object, the companion, was quite red. And it has very unusual colors with respect to brown dwarfs, with respect to old brown dwarfs, typically. So we were already discovering this some peculiar characteristic for these objects. But of course, the contrast that we could reach were very limited. So we could not say that this object is really a planet. It looks like more a binary system, okay? And the mass ratio between the two objects is very different from when you look at the solar system between Jupiter and the Sun, okay? But now we have we are entering a new era. We have new instruments which are much more powerful at looking at very faint planets in the immediate vicinity of the host star. So we can typically find young analogs of Jupiter with these instruments. And you can actually characterize them at the same time. So this is a movie showing one of the data from one of the sub-instruments of the sphere instrument. It's called the EIFS, so integral field spectrograph. And basically, you have seen already some picture. It's an instrument that allows to combine the spectral and the spatial information. So you get simultaneously 39 images of your star, 39 high contrast imaging of your star in at different wavelengths in the infrared. And when you have applied some stellar halo removal techniques, you can reveal a point source in the vicinity of the host star, and you can extract the flux of this point source, meaning that you can get a spectrum. And in this spectrum, you can already find some typical absorptions, like the water band line here between 1.3 and 1.5 micron. But the difference between this generation of instrument and the one before is that you can really detect much fainter objects, very, very close to their host star. We can also, with these new instruments, look at optical wavelengths. So you have Strehl ratios at optical wavelength, the angular resolution, and the contrast to actually get some photometric data points on the spectral energy distribution of the companions. So this is an example with a brown dwarf companion here, a PZ-TEL-B, where we have obtained 2 different data points. You can also actually go down to wavelengths around 650 nanometers. So you can actually look at accretion features, H-alpha emission lines, okay? So we have designed some narrowband filters centered on this line, and we can actually measure the photometry centered on the line. And you can see this is an example with a recently discovered planet, PDS 70, which is a very young planet. And Kevin Wagner, who is here, actually, he obtained these results, and he detected some emission into the H-alpha filter, meaning that the planet is actually accreting, okay? Such a measurements had already been done in the past with the HST WFC3 camera, but for much more distant companion. At wavelengths which are longward of 3 micron, we have very few data. We mostly have some photometric measurements in the L band around 4 micron and the M band at around 5 micron. But the data are, very scarce. There hasn't been any systematic characterization of planets in this wavelength. And it's even worse at longer wavelengths. So if you want to go to mid-infrared, there is basically a very, very limited knowledge. I think 1 or 2 companions have been characterized. This is an example here. Believe me or not, but there is a kind of a detection here of a brown dwarf companion around an A-type star. It's called Eta Tel-B. And the detection is made with VZIR at VLT with some filter centered at on the 8.6 micron PAH line. Actually, I think one of the reference study for the spectroscopic properties at wavelength longer than 3 micron has been published by Stone et al. 2016, where they have characterized several companions. And actually, the spectra, to my opinion, are quite disappointing. They are very flat. But actually, no, they're interesting because in this wavelength regime, you have several absorptions like methane and CO, which can allows you to set some constraints on the non-equilibrium chemistry, conversion between CO and CH4 and vice versa. Due to the enhanced vertical mixing that we are probably experiencing in the young giant planet atmosphere. You can also do some polarization, so some experiment trying to detect polarization on companions. So we know that clouds of silicate grains are forming in most of the in the atmospheres of most of the planets that we are studying right now. And if you have some inhomogeneity in the cloud cover, or if the object is rotating fast, it will become oblate, and then you can have some polarization level that is induced by these effects. And so there's been some prediction. It's very hard to detect such polarization measurements. There's been the talk by Max a few days ago for brown dwarf. But for planets, actually, the only case where we are detecting some polarization is CS-CHA-B, which is a low mass companion. We're actually detecting a high level of polarization. So this high level of polarization means that it's probably not detection. It's not polarization induced by the clouds that we're seeing, but rather some effect due to circumplanetary material around the companion. Okay, so let's go back to some diagrams that you have been seeing in yesterday's talk. So this is a color magnitude diagrams. So where basically you have the sequence of regular dwarfs, so M dwarfs, L dwarfs, which are the old objects are basically these circles, and then you have this sharp LT transition, okay, and then you go to the T dwarf regime, and here this is not shown here, but you could continue here and hide the Y dwarfs basically, okay. And the planets, or the young companions that we are detecting with the directly image method are reported here in black, and you have the young brown dwarfs, which are this object here, and they are occupying a different location in the diagram. They are redder, and some of them at the LT transition are underluminous, okay? And we have this very exotic object here, 51REB, JG504b, and for instance, this one as well is really interesting, 206893b, because they really deviate from everything we know. So I will talk about these objects later in the talk. What's nice, fortunately, in the last maybe 5 years, people have used WISE data. I know that we are using Gaia data as well to identify free-floating objects in the field, so in the solar neighborhood, and that are sharing the same kinematics as some young stars, so young nearby associations. And so this allowed to identify very young brown dwarfs, like with ages below 150 million years, very close to the Earth, so they are relatively luminous objects. We can characterize them. This is an example with the albedo radius association, where a whole sample of objects has been identified, and it draws a sequence in mass. So here are more massive objects, here are really planetary mass objects, and these objects can be characterized very easily with regular spectrographs. So you can have exquisite details on the spectra, and they share the same mass range and gravity and age range as the directly imaged planets. So they are really analogs, and they can teach us about what's going on for our in the atmosphere of our young planets. And conversely, this is here what we have obtained with the Planet Imager instrument. This is a mix of data gathered by GPI and Sphere, the two Planet Imager instruments. And you can see some similarities between these two populations of objects. So red slopes in the L dwarf regime, some methane absorption appearing for some objects here, but still a lot of flux in the K band arising. So this is something due to the collision-induced absorption of H2, which is relaxed, which is lower in low gravity environment. So we'll focus on two parts of the color magnitude diagrams. I will show you very briefly some examples of what we can do right now in terms of characterization and what this implies for the cloud physics. So here is an example with HR8799 was observed with sphere during the science verification of the during the commissioning of the instrument. And when you pile up data, you can suppress the stellar halo and reveal the emission of the planet, and you can really get new information in terms of photometry and spectra on these planets. And so we collected this information. So we got new spectra of the two innermost planets. So this is for the planet E. And when you use the whole collection of photometric and spectroscopic data points obtained thus far, you can actually make some comparison with the population of young brown dwarfs that was identified in the last 5 years. And so it's really interesting because you can find actually analogs in the field of these planets. And it turns out to be also very late type objects at the LT transition. And these objects are also showing some variability. So this means that I think for the planets, it would be really interesting to look for variability, because they are really good candidates for having variable spectral features and photometry. So it's about the same conclusion for the D planets, fitted by the same kind of objects. So these are young objects from with about the same age as the planets, the same mass, and same gravity. So we are understanding from a theoretical standpoint that these planets are not exotic objects, but they are really, they can be matched by non-free-floating brown dwarfs. But that's true for the two innermost planets. For the two outermost ones, we are still lacking the good templates, basically the good empirical templates, the right analogs of these outermost planets. And what we have done in these studies, that we have taken actually we have looked for peculiar objects observed with WISE, and we think that this peculiar T-type object could actually be younger than the population of brown dwarfs. And so we reddened them with hazes of small particles, okay, like some hazes that we are finding on transiting planet, actually. And we can actually reproduce then semi-empirically the spectra of the two outermost planets doing so. Well, there's been some additional study on this using these reddening curves of forsterite and enstatite, for instance. And basically, people believe that, yeah, at high altitude in the clouds, there might be this population of small grains that we are not encountering in regular brown dwarf, but that appears to be there for the young image planet and the young brown dwarfs analogs. There have been also an understanding of these planets from a theoretical standpoint. So here I'm just listing the main ingredients that have been proposed to explain the peculiar properties of the planets in this system. So there have been several papers dealing with the modifying the extent of the clouds in brown dwarfs. So proposing for either thick clouds with particles of a large size, which produce a gray extinction and allows you to explain both the spectral properties and the luminosity of the planet at the same time. That's the big challenge for these planets. Other models, like the one of Mark, are rather proposing that a more self-consistent view of the evolution of clouds with surface gravity, and you can also explain very nicely, actually, the photometry and basically the absolute flux and the colors of the planets this way. Other ingredients have been proposed: patchy clouds. So this, you know, from the empirical standpoint, we're also suggesting that this object could be variable, so this fits well. Non-equilibrium chemistry, so using data points at longer wavelengths, and chemical enrichments, okay? One paper also proposed for an additional ingredient, which is called thermochemical instability, which modifies basically the PT profile of your atmospheres and produce radar spectra. And so these things must be investigated, I think, also for these planets. there's been also some studies to try to determine whether the planets were enriched. To try to find differences in metal enrichment, but also differences in terms of C2O ratio. And basically, they are finding values. I'm a bit skeptical about the conclusion, actually, because this kind of tools, the retrieval tools, they really necessitate a very good understanding of the microphysics of your clouds, and basically on the cloud physics as a whole. Because the clouds that are being formed into the atmospheres of these planets, they are mostly made of forsterite and enstatite, and these are bearing a lot of oxygen. So basically, when these grains are forming, they are depleting the gas phase in chemical elements, and in particular in oxygen. And if you do not model this self-consistently, I think you can really run into troubles when you're running when you're inverting your spectra. So this is an example here with Christian Elling's in Christian Elling's paper, where she's studying how the C2O evolves through the clouds, and you have a correlation between the condensation of the grains and the evolution of the C2O locally in the clouds, in the gas phase. Okay, here's another example. That's a very exotic object. It's an relatively old brown dwarf, discovered very close to a F-type star, and actually the spectrum is not matching anything we know. Like the atmospheric models have troubles to reproduce it. We don't know any young brown dwarfs or intermediate age brown dwarf or old brown dwarfs that matches the colors of these objects. It's probably the reddest object we have ever identified on the sky as a companion to a star. So that's a mystery. Could this object be surrounded by some material? So probably a disk, possibly a disk. That seems very likely because the system is relatively old. Could this object have some supersolar metallicity that we are not fully exploring into our grids? That's a big question. Another exotic object is this planet PDS 70b. It was identified with the SPHERE instrument very recently. So it's nested into the cavity of a transition disk. You can see actually directly the disk here and the cavity. We are seeing it actually moving around the star. It's co-moving with the star, so it's a bound object. The mass is around the one of HR 799 E, C, and D. Well, it's on a wide orbit. And it has very red colors, so we tried to model this color, and actually we are running into troubles. All the fits are converging towards the edge of our grids, basically. So we really also need to understand what's going on for these very, very young objects. Probably that they have very, very low surface gravity, but it might also be surrounded by some materials. Disks around the object could also be emitting. We'll show some slide later in the presentation. So it's, there might be not only clouds for this that object that is producing the red colors. Then let's move to the objects which are a bit colder, so like with a temperature between 700 kelvins and 500 kelvins. Okay, so we're entering the T-type regime where you expect to find methane absorptions, and we're actually finding some methane for these objects. So one of the first actually detected planets with the new planet imager instrument was 51 Erybi, and it was this kind of T-type object. So it was really a breakthrough result. When you look at the spectrum, you can see definitely that there is deep absorption features. Here, this is the methane absorption I'm mentioning, okay, at 1.6 micron. There are also absorptions of water at shorter wavelengths. And basically, from this spectrum, you can extract a lot of information because there are these deep absorptions. The problem is that, as you can see, there is several collections of spectra, and they do not match with each other. One has been obtained with Apai. It has a higher flux at J-band, and this has been obtained with SPHERE, and there is some kind of disagreement. It reminds me a lot about the transiting spectroscopy and its beginning, actually, where there were lots of debates about reanalysis of data and this kind of thing. So this is something that both consortium are working on. We're trying to understand what's going on with this object. The data extraction is actually quite difficult. But then two different studies have been presented that aim to characterize the object based on, well, on one hand the SPHERE spectrum, and on the other hand the Apai spectrum. So when you're using the SPHERE spectrum, you are finding that you need clouds. You need actually thick clouds. you find fits for low surface gravity, so that's basically, that's the view that we have for this kind of object. They should have low gravity. Intense vertical mixing. And it is proposed that actually the planet might have a supersolar metallicity with a metallicity of 1 dex. When the GPI spectrum gets analyzed, the GPI consortium is concluding that actually this object needs models with clouds as well. So actually they have used different cloud models, but one is particularly interesting, and it involves the formation of sulfate clouds, so sulfate and salt clouds, which would tend to appear in the low gravity atmospheres of T dwarf. Okay. So I won't give you any more details, but also finding a more reasonable value for the metallicity, so metallicity closer to the solar value than the one we are finding with sphere. But as you can see, they fit. When you are including clouds, everything fits well, but the J-band here, there is still some excesses emission. So as I said, we really need to understand what's going on with the data first. Yeah, another example that will be actually my last one is JG504. That's either a planet or a brown dwarf, so we'll not enter into the debate. But that's an exotic object because it has red colors, and we tried to understand why it had red colors. So we took some photometry with sphere. It's a very faint object, so it's hard to take a high quality spectrum. So we decided just to take photometry, which has sampled the main molecular absorptions in the near-infrared. And well, you can see that in the molecular bands where the atmosphere is absorbing, you can find the object. Here, this is a water band, so the object is not visible. But then when you're out of the water band, actually, you retrieve your companion. And it's the same for the methane absorption at 1.6 micron. Here, you're out of the absorption. Here, you're inside the absorption. You can see your object. This actually this difference between the two images can be used actually to remove the stellar halo and reveal planets, which are cold. Okay, so we have extracted the photometry of the companion from our images, and this is the green points in this figure. And what's nice is that now we have many more points on the spectral energy distribution of this object at near-infrared wavelength, where we obviously have a lot of spectra of brown dwarf at this wavelength. So we could run some empirical analysis, and the empirical analysis is already telling you that this object is only fitted by some very late T-type objects, which are proposed to have clouds in the atmosphere, while you would not expect to find clouds at this temperature in the atmospheres of these objects. And we verified that actually using models. So we worked with several groups, including the one of Caroline Morley. Caroline is including this formation of sulfate and salt clouds in our atmospheres. And this is really producing, improving the fits to have these clouds included into the models. So this produces basically, this tends to produce radar slope, and really it improves the results, the fit that we are having. We also tried to use some Bayesian inference methods to get some measurements of the metallicity. So to keep it short, we use different models with different hypotheses on the cloud physics, and we are getting very different posteriors. So this tells you two things. Models-to-model systematics must be accounted for when you're deriving very fine details on your object, like metallicity and gravity. And the other thing is that we looked at the literature, and people are not using the same abundances for the solar, the same reference abundances for the sun. So there is kind of shifts in what you inject in your model at the beginning in terms of chemical mixture. So I think people should really talk to each other, the people doing the models, to really have the same, to use the same reference abundances. Okay, so some last slides show some more general statement, and this will probably trigger discussions, is the difference and the similar physical properties between different class of objects. So I discussed about the old brown dwarfs, Yesterday, Julian mentioned briefly that it might be interesting to compare transiting planets and image planets in terms of spectroscopic properties. So let's just have a look at what we know about these planets thus far. So for imaging planets, we know that they have low surface gravity, chemical enrichment, non-equilibrium chemistry. They can have surface inhomogeneity. I mean, Daniel will talk about that later. And for the youngest one, they have accretion signature. Okay. For the old brown dwarfs, they have high surface gravity, chemical. Is there a chemical diversity? Some papers seems to say to answer this question favorably. So yes, possibly. There is non-equilibrium chemistry, and there is surface inhomogeneities. And for the transiting planets, well, basically, the big ingredients that you don't have for the other two classes of objects is the photochemistry. You can then also have thermal inversion, strong transport, okay? But you can also have surface inhomogeneity due to the tightly locked due to the fact that the planets are tightly locked. And you can have also some chemical enrichment. And now, actually, there is something that is common to all these objects, okay? That's the effective temperature. So if you look at transiting planet, at the day side of the transiting planets, there is an overlap in temperatures on the day side with the one of the directly imaged planets and with the one of brown dwarfs, actually. And so it would be really interesting indeed to talk to each other, because there really something to do on the empirical understanding of this class of objects and also for their modeling. So basically, hazes and clouds are forming for these three classes of objects. That's one consequences. But of course, the source of energy behind that is very different from the three different classes of objects. Here's an example. That's the day-side spectrum of the transiting planets WASP 43b. That was published by Laura actually in 2019. And you can see here this very clear detection of water here at between 1.3 and 1.4 micron, rising slope here in the edge band, and here this absorption here that is possibly also due to water. And so you can actually find some image planets that reproduce relatively well the spectrum of this transiting planet. So that's very, very funny to make the comparison. It's VHS 1256b. It's 12 Jupiter mass objects around a pair of M dwarfs. So, well, call it a planet or not, but that doesn't change, yeah, what I'm saying. 1,700 Kelvin, I think, from, yeah, something like that. So, okay, some provocative statement now. So we have made this comparison between image planet spectra and transiting planet spectra. Can we actually do more comparison? So obviously you can also take the example of the young brown dwarfs I was mentioning as analogs of image planets and say, okay, they also look like the one of your transiting planets. But there is another class of objects that is interesting to include in that comparison. This is the F-Orionis objects. So what you're seeing here is the spectrum, the emission spectrum of disk material, okay? These class of objects are massive stars. They have massive disk around them, and the disk is heated at high temperature. It radiates in the infrared. And actually, in the spectra of the disk, you can actually see water band features. You see a red slope. So the question here is, for the directly imaged planets, if they are surrounded by disk of this material, can we distinguish the disk emission from the emission of the atmosphere of the planet? That's a real question I think that the community should address in the coming years. I will go very quickly on this. We have a range of new instruments and techniques that are being proposed and implemented on the present data, but also to prepare the next generation of instruments, and that will basically use the high spectral resolution and also the high contrast capability of the instruments to really detect planets that could have been seen before. Okay, so we'll look at planets closer to the star, much smaller in terms of mass, but also possibly cover different evolutionary stage of the planet. So you could monitor how the atmospheres evolve in time for the directly imaged planet. And that's I mean, it's in 6 years from from now we'll have this capability. Even with JWST, we might have this capability. We could extend our spectral coverage to long wavelengths, so where non-equilibrium chemistry takes place, where you have silicate emission features. So we are going to learn a lot, I think, on the atmospheres of these exoplanets. Okay, and I will just leave you with these slides and some takeaway messages. Thank you. Well, I think it would be nice to make realistic models of the disk, the circumplanetary disk, predict the emission features, and mix that with an atmospheric models, and then generate grids. You will have a lot of free parameters for sure, but we have the tools now to have some constraints on these parameters, study the degeneracy. I think that would be something really interesting to be done, especially for these very young planets. I mean, I was mentioning PDS-70b, but you could take also 2M12 or 7b. You could take all these objects at the altitude transition with ages lower than 20 million years and just do the exercise, basically. That would be really interesting, I think. So, yeah.
I think, like, to compare direct image planets and the transiting planets, their PT profiles are very different.
Yes.
Why should we expect to, like, their emission spectrum to match with each other?
Well, that's a good question. Here, what I propose is really an empirical study of this object, just comparing the spectral features and try to guess, okay, there is this molecules forming, what you can say and what you cannot say. I'm not proposing for deep theoretical understanding based on this comparison. We have actually started to do that with Laura in our paper from last year, and that's really, I think there is a lot of potential to repeat that. So basically, you take spectra on different time on the phase curve, and you try to match to see whether there is some match between the temperature of your transiting planet, the temperature of the atmospheres, and the spectral features that you get when you get a comparison with image companions or young brown dwarfs at this kind of temperature. And actually, this works relatively well, I mean, at low resolution at least. So, yeah.
I don't think you mentioned it, but surely with the transit spectra here, where you've got a peak, that means the atmosphere is strongly absorbing. But for the directly image planet, where there's a peak, that means the atmosphere is weakly absorbing.
No, this is an emission spectrum.
Yeah.
Transmission spectrum.
Which
Yeah.
one?
The transiting planet spectrum is the emission spectrum of the transiting planet.
Yeah.
I think it's great to make those comparisons, but you just got to remember, you know, the irradiated planet stuff can be cold trapped at depth. You can have completely different composition than what you're looking at. So I always get you have to present it and look at it, and just proceed carefully.
Absolutely, yeah. Yeah, I do agree. We all agree, I think.
Yeah, I mean, to first order, they're like continuum emitting at a temperature plus water absorption top. So they're gonna look somehow a bit the same. Then you need the context to know in a transiting planet, this spectrum that has this shape means that, and in a directly imaged planet, the spectrum that has the exact same shape might mean a completely different conclusion, basically.
I think in terms of inputs for the models, I don't know, it would make sense to get a very high resolution spectrum of young brown dwarfs or exoplanets that are directly imaged, and look for departure in the atmospheric models in terms of line opacities, and then use that to improve the models for the transiting planet. That could be some synergy that we could find, actually. So, because we are talking about the same temperature, right? I mean, like temperature range. So, yeah.
For me, this comparison actually kind of means that in the case of not very good data, doing a free retrieval of two objects that look almost the same with very different physics can be dangerous.
Yes. Yeah, I do agree with you pretty much.
Last question. you.
Thank you.
Again. Is anybody in a super rush and needs to leave at like noon exactly the room? Oh yeah, okay. Okay. Sounds that we're okay.
No, it's good. No. It's not supposed to show anything. Okay, so I go with the pro mic. Yeah, thank you, and thanks for sticking around until the end. So I will tell you a little bit about cloud decks and atmospheric dynamics, just continuing on the excellent talk by Mikhail. He showed amazing pictures and photometry and spectroscopy of directly imaged planets, and emphasized the comparisons and similarities and connections between directly imaged exoplanets and brown dwarfs and or Jupiter. So I completely agree with what he said. I just wanted to remind you again of the color magnitude diagram. I don't go into details, but what the equilibrium condensation models tell us about the appearance, thickening, and disappearance of clouds in the upper part of the photosphere. We have understood the complexities in this picture. But what I wanted to highlight here is that although we understand that the primary driver behind this color magnitude distribution is temperature, we understood that there is a secondary parameter here, thicker to thinner clouds, cloud thickness in the visible upper part of the atmosphere. There remains many other parameters that are important. So we have discussed non-equilibrium chemistry, unusually thick clouds, cloud holes, patchy clouds, vertical mixing, different other components that complicate this image. And we do need actually all these parameters, or at least some of them, because what you see here, scatter, that scatter is not measurement uncertainties, that scatter really reflects the diversity of the objects in a given color magnitude part of this diagram. So the key question that I want to explore here is how can we disentangle these effects? And the key issue is that many of these have degenerate effects on the spectrum. You can exchange changes in one with changes in the other. What helps us here are variability surveys. Variability here means temporal modulations in brightness and in spectrum. And it's a relatively early idea, really dating back soon after the discovery of brown dwarfs, that we may find patchy clouds in them, especially in this difficult to understand LT transition, where in a very narrow temperature range, suddenly we see great changes in the colors of the objects. So how is that possible? This remains one of the challenges for models. An idea was put forward that maybe we see in a otherwise thick cloud layers, we see holes, and through those holes we peer into the deeper interior from where higher brightness temperature emission, bluer emission, emerges. So there were a range of attempts to find variability. Many of them identified possible variable sources, but very rarely were there any detections that were, I think, really convincing. So nevertheless, the idea has been around, but I think what really changed the field was this very nice detection by a team led by Etienne Artigau. This basically was very, very clear and very obvious photometric variability detected in LT transition brown dwarf. And so this really, I think, sparked many other follow-up studies, and I will show you some of these. Another nice detection came from Jackie Redigan's survey PhD thesis, an object that remains the highest amplitude variable that we know today, reaching 27% variations. You can see these are data typically taken at different days in different filters. It's difficult usually to collect spectra from the ground on these objects. So these are the most variable objects that were discovered from the ground, but in the meantime, using space facilities that are much more sensitive, we now have well in excess of 50 brown dwarfs that we can study in variation. Let me maybe mention here, and then I will remind you later if I don't forget, that many of the objects, even I call them brown dwarfs, that many of these objects are actually in the planetary mass regime, and many of them actually are best matches, spectral matches, to directly imaged exoplanets. So you will actually see some of the same names popping up than in Michael's comparison, in which, based on the spectra, they identified best matches. So many of these objects are variable, sometimes the same age, same mass, same association, in which the directly imaged planet is found. Okay, so I will not cover all the exciting results from this field. Just there's not enough time, but I refer you to two excellent reviews, one by Beth Biller, the other by Etienne Artigal for other details. So what I will focus on are basically how can we use these rotational modulations to explore clouds, cloud structures, and I show you why this helps. And I think there's a big lesson here also for right away for the transiting exoplanet community too. So the question is, how large a sample do we really need to understand cloud physics, for example, or atmospheric physics, right? And we may think that with brown dwarfs, where we have now thousands of objects, probably about 2,000 to 3,000 objects with relatively high quality data, we are in the position to disentangle all these effects. And that's not the case. So even though we identified, I think, as a community, all the key components, really the interplay between them remains not well understood. There is degeneracy and there is room to explore. So when we determine the sample sizes that we need to really understand the physics, we must consider the dimensionality of the parameter space. And so there's one, let me illustrate this challenge here. So we may think that if we compare all these brown dwarfs, we will find out what are the effects of the different parameters. And a lot of progress has been made on this field, of course, this way. But the issue is that if I take any two brown dwarfs and I compare them, or any two hot Jupiters, or any two directly imaged planets, there will be many parameters in which they differ. Some we can measure, some we cannot measure, right? And they have degenerate effects. So what we do, in a sense, in the rotational modulation community, is that we study different cloud structures in the same atmosphere. When you do that, then many of the parameters are the same because you are studying the same atmosphere. You are looking at differences in the same atmosphere. So that is a trick that allows us to better isolate cloud structure, variations in the cloud structure, from other parameters. So this, I will show you a few select results from this field. Let me show you the first one. Are cloud holes responsible for the cloudy, cloud-free LT transition? So this was a project that we embarked on, and soon after the Etienne et al. Discovery of the first highly variable brown dwarfs, we requested time on the Hubble Space Telescope to take some data. Let me show you the data, and this kind of illustrates the data we are working with. What you see is a spectrum. You have seen spectra like this, mostly from models, but this is an actual observation. This is a high signal-to-noise spectrum, which signal-to-noise typically 400 to 600. Okay, every wiggle here is a real wiggle, and so this is really exciting. I mean, it's just nice to work with an object like this. I should mention this is about just 1,200 Kelvin or so, this object. The other cool thing is that we can do this in just 3 minutes, sometimes even less. So I'm not actually going to show you one spectrum. I'm going to show you a movie of data. These spectral changes are all real as the object turns around in about 8 hours, and we see different thickness clouds turning in and out of the visible hemisphere. Okay, so it's an incredibly rich data cube that we can use to explore what happens if you play with the cloud parameters. So that's very exciting for us. This is one of the many objects that we were able to study this way. So I will really just scratch the surface here, but hopefully touch on the key results. So this is a panel in which similar results are shown for the first two LT transition objects that we studied. This one actually is a planetary mass object. It's probably somewhat more massive. What you see in the top panels, blue and red, are spectra at the highest and faintest states. You see that they are quite similar. Especially if you divide them, you will find that actually the variations in the J band and H band are quite similar. They are also quite similar here. It's almost a flat variation. Since then, we have observed about 4 or 5 other objects in the LT transition, and we always find the same thing. It's a relatively flat, relatively gray continuum absorption that's introduced. I will also, so this is the ratio that's important. Notice that in the water band, the variability amplitude is reduced, and I will come back to that. That's very exciting. Another interesting thing that I will also come back later to is this is the light curve. It's a phase-folded light curve, so our 6th HST orbit coincides pretty well with the first one. you may think, oh, this is pretty noisy data, and you are partly right. This is phase-folded light curves for this SIM0136. Interesting is that the noise here is not in the HST or the detector. The noise is in the brown dwarf. It doesn't phase fold, and I will come back to that too, because that's a very interesting result too. But just for comparison, this is the typical precision of the HST data. The changes you see there are very real. Okay, so if you take color magnitudes, I showed you the J and H band variations. If you compare those, and you can put them on a color magnitude diagram, this is an older version of the color magnitude diagram. Then we were less artistic, but you can see that the changes are along the L sequence. This was very surprising to us because, and I think probably to everybody back then, because everybody expected that what we will see in the cloud, in the transition, LT transition, will be patchy clouds. So you would see basically through holes in the deeper interior where higher temperature, the temperatures are higher, so higher brightness temperatures, bluer radiation would emerge, and you would not have the opacity. But instead of this change, we actually found changes around the L branch. Radiative modeling revealed that we actually have to combine different thickness clouds correlated with temperature variations to reproduce that. No other combination worked, and other studies have reinforced this interpretation too. So instead of cloud holes leading to large color variations, instead of that we find small color variations introduced by cloud thickness variations. No single cloud hole really has been identified yet. So when we think about patchy clouds being there, they are patchy, but our evidence currently is that the patchiness is more in the thickness variations and not through opacity holes through the clouds. Okay, follow-up studies, we focused on how different are LT transition dwarfs, actually, from L dwarfs. So this was a study led by Hao Young, postdoc in my group. So I showed you already, and this comes now, the water band comes in. This is the variability amplitude. That's only now what I'm showing you in the two early T dwarfs that I showed you before. The key point was that in J and H, they had the same level of variations, but in the water band, that was reduced. Okay? And so we went to L dwarfs, and in L dwarfs, when we measured them, and then since then we have a larger sample I'm going to show you, we don't really find significant reductions in the variability amplitude. In and out of the water amplitude, we see the same, essentially the same amplitude of change. So this was, we were surprised, but those were early days. What basically the interpretation here, what we put forward and has been reinforced by other studies, I will show a larger sample, is that this reduction in the amplitude comes along from the fact that from the fact of how deep you are adding your clouds. If you add your clouds deep in the atmosphere, you will have a significant water column for the photons to travel through. Water is well mixed in these atmospheres. Whereas if your clouds are high up or you have high altitude hazes, there will be very small, shallow column to travel through. So there will be not much opacity difference in and out of the water. Okay? So this basically, in a sense, it's very similar to when we do Earth observations and we can use different wavelengths to probe how deep the clouds are, or what Pat has been showing about the solar system planets. We can play the same trick with water band in and out. And so this is something that we published. We are arguing that in L dwarfs, at least based on this small sample, there must be high altitude hazes or high clouds. With an earlier versions of models by Mark's group, we were not able to stretch the clouds high up enough, but with the new models, as Ben Liu has been showing, this is now possible. So this is quite exciting. In a new paper that we are submitting just a few days from now, we extended this sample. So now you see many more objects stretching from mid-L all the way down to T6. And maybe it's a good point to mention that maybe not everybody expects clouds in T6 objects, but we do see variability that comes from clouds. So they have been there, and they have been there at least from 2012. So when the first variations were detected. So okay, so what you see here is basically, although just by eye, is that the reduction in the water amplitude is increasing towards decreasing temperatures and spectral types. So this is nice. This basically provides us, as I showed you, basically a kind of a proxy for the pressure at which the clouds are located. We can use state-of-the-art models, in this case from Mark, to translate, basically assess what pressure levels we probe, what is the contribution of different pressure levels to each of the spectral bins that we have in our spectrum. And from that we can basically quantify what is our expectation for the depths that we are probing. You see we probe deeper in the J and H band, and we probe shallower in the water band. This is of course model based, but nevertheless the general trend with the opacity is very clear. So you can plot it as a spectral type, and then basically the integrated relative water band modulations, which what all it means is that how large is the orange shape here, how deep are the clouds. And this basically verifies that with early spectral types, we don't have deep clouds. All the clouds in the early spectral types are high up. This is not new, but what is new is that this is basically an independent model that really uses opacity differences within the same atmosphere to show that this is the case. So we were excited about this. Another nice study that has emerged from Bess Biller's group, this was led by Joanna Voss, was to compare objects V sin I measurements, so what is the rotational velocity and projection of brown dwarfs, with colors and with rotational periods that they measured. And then from that they argued that there's actually a trend. They are suggesting that objects viewed equatorially, equator on, are bluer in the near infrared. So they are suggesting that actually clouds are thicker closer to the equator. So this is an interesting result. Earlier with Stan Metchev, we have also, based on Spitzer data, we have also noted a tentative correlation. So we yeah, so basically in this case you would be 0 would be if you see it equatorially. Okay, so let's move now on towards lower objects and explore a little bit more the role of gravity. So I mentioned temperatures and cloud thickness as being the key drivers. We have heard that we expect cloud thickness to play a role, and we have shown evidence for that. There is, of course, good reasons to believe that. The pressure scale height is inversely proportional to the gravity. So we may think, and it makes sense to think, that low gravity results in thick clouds. This is one very viable possible explanation for why we have these colors for the directly imaged exoplanets and many of the brown dwarfs that I will show you. But there are also other possible contributors, including mixing. So Ben Lu gave a short talk. I just wanted to highlight again this extremely red object, which was also one of the best comparisons for the HR 8799 planets. And Ben has done really nice work with, he discovered a really large amplitude variability there, which is interesting. It fits in a pattern. Many of the objects where we find really large amplitude variability are actually very low mass, non-planetary mass objects, or best analogs to them. So that's, we didn't prove that statistically, that there is a correlation, but it looks very, very interesting. I will just skip this, but Ben has noted basically a correlation between the slope of the variability, so the color trend introduced by the absorbers, and the amplitude of the variability. Objects with more colors, maybe smaller grains, most likely, have larger amplitudes. Bess Biller's group has detected modulations in a planetary mass object too, first from the ground and followed up with Spitzer. And a very nice result, PSO J13. This was also one of the objects that Mikhail mentioned. In another study, Ifa and Joe, sitting here, observed 2-1207b. So this is the 4 Jupiter mass object that Mikhail also mentioned. We used HST, we rotated HST, and we removed the brown dwarf here. We were not interested in this brown dwarf. We're interested in this planet around the brown dwarf. And we could get sub-percent precision photometry for the companion, and we've showed that this is actually variable. This is simultaneously obtained two-filter photometry. So we could compare now the rotational modulations, but more importantly, the colors of the clouds that are introduced by the clouds there. So this is something that's part of the Cloud Atlas program, an HST Large Treasury program, in which we are building up a large sample of very low mass objects and higher gravity objects, and we are comparing cloud properties through variability in these. So probably in Cloud Academy 2, I will be able to show you how the cloud properties depend on the gravity. Okay, so there is also ongoing work by us and others to push extreme adaptive optic systems in the threshold of being able to pick up very small variations, and there is exciting work. This is a paper we published in 2016 on methodology, on planet-to-planet relative photometry, and there are really exciting other works in the pipeline. The last topic I wanted to bring you to is one that I'm very excited about. This is atmospheric dynamics. And so this is something that clears up a lot of confusion. I think it allows us to connect exciting pieces in this puzzle. So it was known from the beginning on, from the discovery, that light curves may change, right? You see a few examples. I already showed you this noisy light curve in which really the object has changed while we were observing it with HST. The problem is that in most cases when you have ground-based data, you are limited by windows of observations, you are limited by systematics, and it was not always clear how do you interpret lower signal to noise data. Plus, data like this existed only on 3 objects. So the question remained whether or not we are seeing giant storms developing, or what is really going on. Complications were the fact that different groups using ground-based data were disagreeing on if the light curves are changing, whether you see a single peak or a double peak, whether the variability amplitude measures were inconsistent, not always, but often. Systematics were questioned. Some of the sources were found to be variable by some groups and not by others. And so we decided that we need to understand what physical chemical processes drives these light curve evolution, whether or not it's common, how it changes. So we launched the Spitzer and HST coordinated program that allowed us to monitor brown dwarfs for over 1,000 periods, rotational periods, over a year roughly, in different 8 visits. And in some of these visits, we had also HST spectral mapping, so we could better connect physics with the rotational modulations. Okay, so I'm going to show you just a small snippet of the data. We have much more of the data, and it's really exciting. You don't see the data yet. What you see is time on the x-axis in hours. Y-axis is the normalized brightness. You will see 2 types of symbols, blue and red. Blue shows the photometric measurements in the Spitzer channel 1, the shorter wavelengths, and red shows in channel 2. We switch back and forth to disentangle color effects from temporal variations. And Hao Yang led the first data reduction, and we published most of the data with interpretation in last year. So this is the same object, different visits. You can see, first, the data quality is amazing. You can see changes, right? And we go back, and this is my favorite part. I love to watch this. What you see here is the same object, and you can see cases when it's a single peaked, and when it's double peaked. You can see times when it's non-variable and times when it's variable, right? So everybody in the community was right when they disagreed whether something is variable or not, or single peaked or double peaked. Okay, a few people were wrong, but they were most of the community was right. The objects don't behave as simple as we would think. These are not sine waves, but much more complex. The amazing thing is that every single visit of every single object that we have taken looks qualitatively like this. It's not completely chaotic. The system has clearly some memory. You see an evolution, but it's evolving on a time scale that we can observe. So this was really exciting. We had all these models ready to fit the light curves with elliptical spots. We could do dark spots and we could do light spots, and we showed that this model works very well for Jupiter. But it doesn't work so well for brown dwarfs. What you see is that if you add the elliptical spot, whether it's dark or light, you always get basically a positive or a negative feature, right? Depending on what you add. It's always asymmetric. It's intrinsically asymmetric. But if you look at these light curves, they always go positive and negative, and there's not a clear asymmetry. You cannot say that these are dark spots or light spots. So because we had so much data, a single one like this, any single rotation, we could fit with a combination of spots, right? But if you try to fit many rotations, there was no way to move the spots around fast enough. We would have needed supersonic rearrangements of the spots that we thought would be rather evil from the brown dwarfs to introduce. So we looked for something else, and we noticed that if you introduce sinusoidal modulations, just a wave, that translates in the disc-arranged light curve into a sinusoidal brightness modulation. And actually, we found that that describes essentially all our data. What you see here are waves fitted, and if you subtract the model, you see just 4 little blips remaining. These are basically what we interpret. These are the spots. These are the asymmetric features. So this is one spot that's in an object that's otherwise dominated by waves traveling around the atmosphere. So we can fit all of them. This is a simpler analytical fit. Theodore Carlidi has done a really nice job in an MCMC optimized, pixelized model that's very fancy and validated, and we get the same results. So it all works very well. Artists were impressed, and they had an impression. I'm not completely impressed by this, but anyway, you can get the idea. The key point is that the waves have slightly different rotation period, and because of this, they are beating. Beating means that when they are in the same phase, their amplitudes add up, and when they are in opposite phase, they cancel out, in effect. It's known in acoustics, and you can see them in brown dwarfs. So first we thought this may be a bit crazy, but then we realized, in fact, Neptune has a similar appearance with belts. Even though this is reflected light, this is thermal emission, but we know that there are banded structures. We know Jupiter, Pat has shown this image, and others too, has bands in it, so it's not that crazy to think that brown dwarfs will have bands. But the strongest evidence came when we took basically the power spectrum equivalent. What you see here are the bands in the brown dwarfs. They are split around what we think is the rotational period, the reference period, and then it's very similar in Neptune. This is K2 data from Kepler in reflected light, but it basically mirrors the same kind of behavior. So now we have, I don't have time to go into details here, we are running out of time, but there were shallow water 2D models from Adam Shulman and Shi Zhang, demonstrating that in fact you expect a jet to emerge if in a fast rotating configuration. Now there are 3D atmospheric models that create banded structures in brown dwarfs, and in a new paper that's under review, a new model was proposed by Shan Yun Ten for radiative convective driven cloud variability, where basically clouds form at the radiative convective boundary, and when you introduce clouds, you change the opacity that pushes the pressure temperature profile to change. You heat up, and when your temperature is increasing, you are moving up your cloud top, you begin to evaporate your clouds, driving an instability that will lead to rapid cooling and then the collapse of the cloud layer. And they can get, in this 1D model, very nice, basically spontaneously introduced variability. So I think we have a new picture emerging for brown dwarfs and directly imaged exoplanets, in which we see cloud tops going deeper and deeper with decreasing temperature, and we see most likely banded structures, maybe equatorial bands in which planetary scale waves are traveling around. So I think overall we have made really significant progress over the past 5 years. Putting the pieces together, we now understand how the artists should depict brown dwarfs. They should have probably belts and waves. So in terms of science, what we learned, we have found that there are significant cloud thickness variations in all of the objects. There is no evidence for a real true cloud hole. We find planetary scale waves to be very common. There is evidence for bands and zonal circulation to be present that may be explained by cloud instability. And this is, most of these apply or should apply to planetary scale objects and directly imaged planets too. Thank you.
That was beautiful. Anybody wants to comment on the RTC questions? Any questions?
Yeah. Maybe this is a stupid question, but I'm a modeler, so I
No, no.
have you ever thought about whether it would ever be possible to detect lightning on?
So yes, we thought about it, but there was no real good way of well, so actually I should mention, of course, Christian Helling's group has been working on it quite a bit. So there are specific model predictions for how the lightnings would look like. We spoke about this at some point, whether we could use HST. I think we need to complete the discussion. As of now, I don't think that anybody has really measurements that were really constraining. Yeah. That's right, yeah. You could look for the chemical byproducts. And yeah, that's right. Yeah.
Has it been invented to detect
Radio, yes. So people have done radio observations, but I think longer than the channel 2, not to my knowledge. So I think it, yeah. And I think that's just because of Spitzer running out of cryogen. But James Webb, I didn't mention, but we and others have worked on predicting what James Webb would do, and unsurprisingly, James Webb will be awesome for this. But yeah, there are some radio detections that allow that add additional information in some cases, primarily for the earliest spectral type objects that I typically did not include here.
Is there any GTO time dedicated to variability monitoring?
For James Webb? Yeah, so yes, I think it used to be not the case, but over the past years these were added, so I'm happy to see that many of the interesting objects will be observed. But I think the other side of it is that the GTO time, so James Webb is not the most efficient telescope, overheads are really very significant, so I think even with the GTO time, only a few objects and only a fraction of the science will be done. That's what's possible. So yes, so basically that's a good point. So I here was focusing typically on L5 objects and later, and that's a choice that we make. In those temperatures, basically the ionization levels of the atmosphere is thought to be pretty low, so it doesn't couple strongly to the magnetic field. So you would not expect the atmosphere to be driven by the magnetic field. So that is the case for, I think, L0 objects. In those cases, you can see in a very few cases when there are detections, you can see basically a very periodic beating. There's a study by John Hizis where they used Kepler data and showed that the brown dwarf had a completely sinusoidal modulation over 5 years and thousands of periods, no changes at L0. And that's best explanation for that is that at L0, M9, you are coupled to the magnetic field. Yes. Yes.
Is it possible to?
It's
Like, what would we need to do?
so it's so there are multiple things you could do at low resolution and higher resolution. So so intermediate resolution. So with James Webb we will be able to do intermediate resolution. So what I showed you was all continuum opacity. From the very beginning on, we have been looking at, for example, variations in methane, and we have also looked in variations in sodium, which we can actually see there. Higher resolution would help, not a factor of 2, but a factor of 10 would definitely help. So then you could look for gas phase abundance variations. If you go even higher, further, there are further possibilities because you can delve into other more detailed information. I should mention that Stan Machev's group has published a paper last year where they had seen evidence in high resolution spectra for sodium variations. So yes, you could assess then gas phase species and then couple that information also with retrievals that you can execute on these data sets. Yeah. Mm-hmm.
Would you expect variability in the core of the, because your sensitivity mostly to the core of the lines, and this is probably above the clouds. Would you still expect variability?
So I would some models predict, for example, methane variations, methane CO abundance variations. For example, if you this fingering instability, fingering convection model, I would expect there that actually I would expect that we would have already seen methane variations, and we have not seen any significant variations in methane. We can with some modeling, we could put, I think, a pretty sensitive upper limit to how that changes. But with a higher spectral resolution, we could look even closer. So I don't know if I would really expect very large variations in as my baseline, but there are models that could be. I know.
There must be a set of lines at high resolution you could find that are just the right line to say which clouds you're going through, or
Mm-hmm.
how exactly tuned to
Yeah.
see
Yeah.
down at the cloud top, and then you
Yeah.
can see those lines.
Yeah. That's right. I should mention that with Esther Brunsley, we published a paper in which we looked at FEH lines in a shorter grism also. So that's and we didn't see that change any differently from the continuum. So.
I think we can give a big
Oh,
shout out
okay.
to Daniel or the organizer.
Yes, yeah, thank you. Yeah, let's. So, thank you. Let me just ask the other organizers to stand up so that I happen to be here, but they have really done an excellent job. And so thank you. And very importantly, thank you all for coming. I think we from the organizer side, we have been really impressed by the quality of the presentations and the discussions and the friendliness of the crowd. So we decided to try to do a Cloud Academy too. I already gave that away, but we hope that sometimes in the near future we'll be able to welcome you again, either here or another nice location. Thank you. That's it. Yeah, you can go.
That was good. Good talk.
Nice.
Fast, but good.
Yeah, there was not much time. Yeah.
Some of the